Okay, hello everybody. So let's compute the three-dimensional volume of the three-dimensional sphere that lives in four-dimensional space, namely all the points in 4D that satisfy this equation. Okay, so let f be the function that sends a point in four-dimensional space to the number 1. Then the volume of the three-dimensional sphere is equal to the integral over the three-dimensional sphere of the function f. Okay, since S3 is a three-dimensional curvy object, in R4, we need to parameterize it. And integrate in the parameter space. Okay? In fact, what we'll see, and I'll draw a little picture here, is that we'll integrate over a certain prism, rectangular prism, that goes from 0 to 2 pi here, and then negative pi over 2, well, here, I'll just write it out. 0 to 2 pi cross. Negative pi over 2 to pi over 2 cross. And this is the third dimension will be, again, negative pi over 2 to pi over 2. And so this will be really easy. So our first dimension will be theta 1, our second dimension will be theta 2, and our third dimension will be theta 3. And we're just going to integrate in any order, actually, because this is a rectangle, we can do it in any order. So why don't we just integrate theta 1 from 0 to 2 pi first, theta 2 from negative pi over 2 to pi over 2, and then theta 3 from negative pi over 2 to pi over 2. And what are we going to integrate? Well, since the function up here is just the constant function having value 1, then whatever our parameterization map is that sends this rectangle to the 3-sphere inside of R4, G, then f after G is just going to be 1 again. So we're just integrating the function 1, and the only thing we need to do is account for the volumes from this nice, easy to integrate region, to the volumes there. And so, well, I wrote G twice, so I'll write G distorts volumes. And so we just need the square root of the determinant of the Gram matrix. This turns out to be a way to write the Gram matrix in Math 250, linear algebra. But we've just been writing in words Gram matrix of maybe dg. Okay, and so this is the change of volume factor. Okay, that is the only thing we need to figure out. Once we have this, we immediately will be able to write down this integral. Well, once we have this map. Okay, so there's two things we need to figure out. We need to parameterize the three-dimensional sphere, and we need to compute this volume correction. So there's two things. Okay. To parameterize, revisit the two-dimensional sphere inside of R3. And so I'll do that with a picture. So here's a rough picture. Now let's take this point right there. And that point, we're going to call it V. Well, we're going to call this vector V. And I think you'll agree that since it's on this equatorial, this circle at z equals 0 height, it'll have formula cos of theta 1, sine of theta 1, comma 0. Okay? And then up here to the North Pole is the vector, well, what's this vector? 0, 0, 1. So, now rotate V up into the third dimension. And by a formula, what I mean is, maybe I'll switch to a formula color, is we're going to look at this plane spanned by, it's kind of hard to draw this plane, spanned by this vector and this vector, and they give a plane. That plane sort of slices through the sphere in a great circle. And we're going to just rotate in that circle. Okay, so we're going to take cosine of a new angle, theta 2, the rotation up or down in that circle, times V, plus sine of theta 2 times, well, this second dimension of our plane that we sliced. And in this way, we get the formula, well, maybe I'll just, sometimes I like to do it like that. We get one formula that sends theta 1, theta 2 to what vector? Well, cos theta 1, cos theta 2, sine theta 1, cos theta 2. That's from these components. And then there's nothing from here because of the zeros. And the third component, all we get is a sine theta 2. And this is an element of the sphere inside of R3. Okay? And so you see that what we're doing here with a theta 2 angle is we are just lifting this equator circle up to some other circles. And as theta 2 goes from 0 up to positive pi over 2, we approach the North Pole, lifting and then, as theta 2 goes down to negative pi over 2, negative 90 degrees, then we're getting circles that are closer and closer to the South Pole. Okay. But this then shows us how to repeat this. Now we just append, so now let V equals cos of theta 1, cos of theta 2, sine theta 1, cos of theta 2, sine of theta 2, 0. And the fourth dimension is in this direction. And rotate by theta 3, by a new variable, theta 3. This will give us our map, theta 1, theta 2, theta 3, being sent, and I'm going to call this little g, to what? Well, we need to rotate cosine of theta 3 times this vector, and sine of theta 3 times this vector. And we're just going to pull the entire sphere up or down and get new spheres, new two-dimensional spheres within the three-dimensional sphere. Okay, so that's C1, C2, C3, S1, C2, C3, S2, C3, and then over here we get a sine of theta 3. Okay, that's G. So this is a map from R3 to R4. And actually, it gives us the entire three-dimensional sphere. When you think about how it works in the two-dimensional case where we lift a circle sort of up or down, that explains why we can take the second and third dimensions from negative 90 degrees to positive 90 degrees. We're just lifting it up or down into the next dimension. Now, the first dimension needs to go from 0 to 2 pi because we need to get the whole circle. And we're going to lift it. Okay. Great, so now we're done with this part. We have parametrized the three-dimensional sphere with this map. Okay. Next, we just need this change of volume factor. So I'll just write in words. Okay. So now we just need this change of volume factor. Remember, that's the square root of the determinant of the gram matrix of the columns of the Jacobian of the derivative of this parametrization map. Okay, so we can take the derivative. Let's call W1 to be the vector that takes the derivative in theta 1 of all four of these. Okay, so the derivative in theta 1, I'll say d theta 1. And what is it going to be? Well, derivative of theta 1, theta 2 and theta 3 are ignored, and a cosine becomes minus a sine. Minus a sine. Now, the theta 1 derivative takes the sine and becomes a cosine. There is no theta 1 and no theta 1 in these third and fourth components. Okay. W2 is partial theta 2, the second input variable. Take the derivative in theta 2, and right here, a cosine becomes minus sine. Here, a cosine becomes minus sine. Here, a sine becomes a cosine. And this has no theta 2, so the derivative is 0 there. Finally, W3 is partial the third input variable. Now I take the theta 3 derivative, and up here, this cosine becomes a minus sine. Cosine becomes a minus sine. Cosine becomes a minus sine. This needs to be a better 3. There we go. And a sine becomes a cosine. Okay. So now we need to take the square root of the determinant of the gram matrix. So we first need the gram matrix. Well, the gram matrix, remember, is W1.W1, W1.W2, W1.W3, W2.W2, W2.W3, W3.W3, and then these three are actually the same as these three. So, okay, we can compute this. First, let's get rid of this. And let's compute W1.W1. Okay, so sum the squares, and we'll get S1 squared, C2 squared, C3 squared, plus C1 squared, C2 squared, C3 squared. Now notice that I can pull out this common factor in both, and that will give me a C2 squared, C3 squared times S1 squared plus C1 squared. This is 1, and so at the end I get just this factor. Okay, that is w1 dot w1. Let's take w1 dot w2. Okay, so now I have to take the dot product of these two vectors. Okay, multiply the first components, and I'll get a positive S1, C1, S2, C2, C3 squared. Now I take these two components, and what will I get? I get a negative S1, C1, S2, C2, C3 squared, and wow, this is wonderful. They are exactly the same, so they will cancel. Now this I multiply and I get 0. This I multiply and I get 0. And so this whole thing is 0. Wonderful. Let's take w1 dot w3. So now I'm looking at this vector and this vector. Okay, multiply the first components and I get positive S1, C1, C2 squared, S3, C3. Multiply this and this, and I get a negative S1, C1, C2 squared, S3, C3. Those are the same. They cancel. Now I multiply this with 0, and this with the 0, and that gives plus 0, and this is 0. Wonderful. Let's do the next one, w2 dot w2. So I sum the squares here, and I'll get okay, so let's look at these first two terms and see if we can factor something out. And I see that we can. So we can factor out the S2 squared, C3 squared, leaving a C1 squared plus S1 squared, which is 1. We still have a C2 squared, C3 squared. Okay, but then, okay, so let's just rewrite this. Notice we can factor out the C3 squared from both sides and get, which leaves an S2 squared plus C2 squared times a C3 squared, and this is 1. And so at the end, we have a C3 squared. That is w2 dot w2. Okay, let's do w2 dot w3. Okay, so that's these two. Multiply and add. Okay, let's see here. Notice we can factor out the common factor right there, which will leave C1 squared plus S1 squared. So all of this is going to be C1 squared plus S1 squared times S2, C2, S3, C3. And then we still have this one, minus C2, S2, C3, S3. So this becomes a 1. And then these two remaining factors, we look at them and we try to say, what can we do with them? Well, they are the same, except with a minus sign. And so all of this is equal to 0. So this became a 1, and then these remaining two are identical but opposite in sign. Last one. So that, that also means that this is 0, this is 0, this is 0. We only have w3 dot w3. Equals. Okay, so let's look up at w3. We have to take the sum of squares. Okay, now let's look at here. Let's factor out the C2 S3 piece from both, and we get a C1 squared plus S1 squared times this piece, we pulled it out, and copy the rest. There's this plus this. Now this becomes a 1, and we get C2 squared, S3 squared, plus S2 squared, S3 squared, plus C3 squared. Okay. Then let's factor out the S3 squared from these two, leaving us C2 squared plus S2 squared times an S3 squared plus C3 squared. This becomes a 1, leaving this, which becomes a 1. And so all of this is equal to 1. Not 0, but 1. Okay, here's our 3 by 3 gram matrix. Okay. Now, all the entries are 0, except the entries on the diagonal. And so the determinant of this matrix is just multiply these entries on the diagonal. 1 times C3 squared times C2 squared C3 squared. Okay. So the determinant of the gram matrix of W1, W2, W3 was equal to, and let's take the square root, and then let's take, what was this determinant? It was these 3 multiplied, so it's a C2 squared, C3 to the 4th. Look at that. You see how these 2 multiplied together give a C3 to the 4th? We multiply by 1. Okay. And C2, C3 squared after the square root. And that's it. That's the change of volume factor. And so our final integral says that volume of S3 is equal to the integral from theta 3 equals negative pi over 2 to pi over 2, from theta 2 equals negative pi over 2 to pi over 2, theta 1 equals 0 to 2 pi. That was our original circle where we had to circle all the way around. And we integrate the function 1 times the change in volume factor, which is the cosine of theta 2 times the cosine of theta 3 squared. That's it. You can now plug this into the computer and get the volume of a 3-dimensional sphere. I'll say the 3-dimensional volume. Okay. Looks pretty good. There were 2 parts. There was the parametrization of the sphere, and then the calculation of this change in volume factor.